Today we're going to talk about electrons and excited states. Everything that we've talked about up until this point has referred to an electron in a ground state. So all of those electron configurations are when those electrons are right where they are typically going to be in that ground state. So when they're in the ground state, they obey three rules that we're going to look at. And you've seen these three rules already. Aufbau's principle is the first one, and that just says that these electrons are going to enter orbitals of lower energy first, and then they're going to come back and fill up the higher energy levels. And I know you can't see this at home, but I have electron configuration written on the board that everybody's looking at. And what we can see is that something like, out of this, what has the highest energy out of these? How would you say which orbitals have the highest energy? 6s is the highest energy level. So that's going to be my valence electrons. So I've got, for example, for those written at home, it says blah, 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 5p6, 6s2, 4f14, then 5d10. And the question is, which has the highest energy? Well, this is the highest energy level, which is really different, meaning that there's two valence electrons. But if we're talking about highest energy, this is the order of increasing energy. That's according to Aufbau's. So all of the stuff that we can't see, it starts off at 1s2, 2s2, etc. And so it goes in order of increasing energy. So a 5d has more energy than a 4f, which has more energy than a 6s. And that's how you would look at that. So Aufbau says that you fill in order of increasing energy. So the lowest energy first, and then the higher energy later. And then Hund's rule. This is our school bus rule, and those electrons are going to enter those orbitals of equal energy one at a time into those orbitals, and they're all going to be spinning in the same direction, so those arrows are all going to be up arrows, and then they come back and fill them in later on. And finally, Pauli's exclusion principle says it's not possible to have four quantum numbers that are all the same within one, for two electrons within one atom. They would have to have something different about them. So it wouldn't be possible for them to be in that same orbital with the same spin, so with those arrows going in the same direction. Okay, question really loud.
It seems like a lot of boxes in our homework and on our notes have a lot of all those things.
So if you're talking about today's notes, that's what we're going to be looking at, and we're going to see why they violate it. So the question or the comment was that that those things were violated, and that's what we're going to be able to make note about that in our homework today. Okay, so when electrons in the ground state absorb that energy, we know that that's considered, they can jump to an electron level that's an excited state. They can't stay there for very long before they fall back down to their ground state and release energy in the process. But we can illustrate the orbital spin diagrams of an electron in an excited state. And by doing so, that electron is going to violate one of these rules, Aufbau's principle or Hund's rule. However, Pauli's exclusion principle can never be violated. It is not possible to have two electrons within that same atom have all four of those quantum numbers be the same. So that is actually impossible. And then on our practice, all we're doing is going through and stating some things. We're going to decide whether or not it's in the ground state, an excited state, or just not possible. So in this first example that we see, do we see anything funky about it? No, it looks fine. We've got, and in fact, what you should be thinking to yourself is that that's an s orbital, and then this is a p orbital of some sort. And we see that our s up, down, then our p up, up, up. So all looks good. So all we're going to say is that that is the ground state, and there is no violation. Ground state. Okay, second one though. Anything look odd about this one? Yeah, the down arrow right here. So do you think that that's an excited state, or do you think it's impossible? It's an excited state because it violates what? It violates Hund's rule. Good. So Hund's rule would tell us that everybody gets on the school bus and sits in their own seat in the same direction, but this guy's not like the other. So it's violating, even though these orbitals are orbitals of equal energy, they need to all have that same spin to minimize that repulsion. So that's violating it. Okay, number 3. Impossible. Why is that? Good. Okay, good answers. Same 4 quantum numbers, 2 electrons in the same orbital with the same spin. That's not going to be possible, so that's a violation. Whenever you have something that's impossible, it's because it is violating Pauli's exclusion principle. Okay, number 4. Excited because we see this guy is not like the others. And what violation would that be? Hund's rule. Don't you wish all lessons were this easy?
It'd also be a violation because instead of putting 3 blocks, there's 5.
Yeah, this is just a situation where you have an S to a D. So it might be something like your 4th energy level, a 4S, going to a 3D. So that one's okay. That's okay. Okay, the next one, what do we think? Impossible, why? Right there. So we see those double arrows, mean that it's violating Pauli's. Okay, I like this next one.
No, it's excited.
I'm hearing ground and excited.
Excited because of Allen's principle.
Okay, so you guys are all correct in that it is possible, but is it ground or is it excited? Let me see if I can spark some thoughts here. Okay, good. So you guys are thinking about your exceptions. So this works because this is an S and this is a D block, and this only works because it's a D block. Give me an example of what this element might be. Could it be copper? Chromium. Okay. Chromium or any of the other guys underneath there, molybdenum or tungsten. So this is actually considered a ground state because it is one of those exceptions that we learned about on that second day of electron configuration. It can't be copper because copper would be expected to be up, down, up, 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 down, 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 and then that's when one of these guys goes away and it becomes a down here. So we don't have enough electrons on that one. Okay, so then we get to our next one. What's that going to be? Excited. Just like you guys can tell. Okay, and why would that be? What's the rule? Aufbau. Because Aufbau's principle says you got to fill up this orbital of lower energy before you can move on to these orbitals. So that's going to be Aufbau. And then the last one. It's another excited one, and it's violating. And I heard both. Let's make sure we understand why it's not an Aufbau violation. It's a Hund's violation. I know you might be tempted to say it's not doing lower energy before higher energy, but remember, all 3 of these have equal energy. But Hund's rule says that they have to all go in one at a time into orbitals of equal energy. So this is a violation of Hund's. And then I think I'm going to turn the video off, but we're just going to, you should be able to do these as well.